At absolute zero, a pure silicon crystal is completely locked down. Every single atom is fixed into a rigid, diamond-like geometric grid. In this state, there are no loose particles to carry an electrical current, making the material a perfect electrical insulator. That rigidity comes directly from covalent bonds. Silicon has 4 outer, or valence, electrons. It shares those 4 electrons perfectly with 4 neighboring atoms, forming tight energy links. Every slot is filled. There is no room for movement. But we can disrupt this perfection by injecting a specific impurity, an atom of boron, aluminum, or indium, directly into that pristine lattice. These specific dopants are trivalent elements. They only have 3 outer electrons available to share. When they force their way into the silicon grid, they can only complete 3 of the necessary 4 chemical bonds. That 4th neighboring silicon atom is left with an empty space, exactly where an electron should be. Quantum physics treats this vacancy as a discrete unit called a hole. Since it marks the absence of a negatively charged electron, the hole behaves, mathematically and physically, as a mobile positive charge. This is the engineering behind a p-type semiconductor. By building an architecture out of a void, we turn a vacancy into an active engine for electrical conductivity. To see how an empty space carries a current, look at the adjacent atoms. The silicon lattice vibrates with thermal energy. An electron from a neighboring full bond can jump over to fill the empty hole left by the trivalent impurity. When that electron moves, the original hole is filled, but a brand new hole is created exactly where that electron used to be. As the bound electrons shift, the positive hole moves into the new vacancy, traveling smoothly through the material. Because our trivalent impurity atom grabs a neighboring electron to finish its own chemical bonds, we classify it as an acceptor. Once it accepts that extra negative electron, the previously neutral core becomes effectively negatively charged. Engineers map this out using a shorthand schematic: rows of negatively charged acceptor cores, which are heavy and permanently fixed in place, each paired with its freely roaming, positively charged hole. While it appears that a swarm of positive particles is darting around, the reality is a cascading sequential movement of bound electrons shifting from one vacant slot to the next. This is a chart showing the energy band diagram of pure silicon. At the bottom is the full valence band, where bound electrons reside. At the top is the empty conduction band. Between them is a massive energy gap that requires significant energy to cross. Doping the silicon introduces a completely new energy state to this landscape. The acceptor impurity creates a precise new band, labeled EA, sitting just slightly above the top of the valence band. This creates a quantum shortcut. Electrons no longer have to make the massive leap to the top band. Ambient room temperature heat provides enough thermal energy for valence electrons to hop up into this low-hanging acceptor level, leaving billions of mobile holes behind in the valence band. This creates an extreme population imbalance. In a doped p-type material, these positively charged holes become the majority carriers, vastly outnumbering the microscopic sliver of free electrons, the minority carriers, that manage to cross the entire gap thermally. By manipulating the atomic energy landscape, we enable high electrical conductivity without the need for intense heat or massive voltages. When you apply an external electric field to this material, that entire cloud of holes stops wandering and drifts uniformly toward the negative potential. Curious, this raises a question about the material's net charge. If the silicon is flooded with positive holes, shouldn't the crystal itself become positively charged? The semiconductor remains electrically neutral. The positive charge of every roaming hole is exactly balanced by the fixed negative charge of the immobile acceptor atom core left behind in the lattice. As these carriers drift, they eventually intersect. A minority free electron will eventually drop into a moving hole, destroying both in a process called recombination. At thermal equilibrium, new electron-hole pairs are generated by ambient heat at the same rate they are destroyed. On its own, a block of p-type silicon is a conductor, but it becomes a logic gate when fused against its mirror image, an n-type semiconductor. By isolating the mobile hole, we strip away the rigid limits of pure silicon, gaining the ability to control the direction and flow of electricity at the atomic level.